linear equations and matrices. Suppose m and n are positive integers. An m by n matrix A is an array the form A equals, and then there's a bunch of entries. The entries in the first column are labeled with the second digit as 1. In the second column, the second digit will be labeled 2, and so on. As we go down the rows, the first entry increments from 1 to 2 all the way up to m. Each of these aij's is a real number. Matrix A has m rows and n columns. The real number aij refers to the entry in row I and column j. A matrix that's 1 by n, that's 1 row and n columns, is called a row matrix. And a matrix that's m by 1, that's m rows and 1 column, is called a column matrix. The set R, m by n, is a set of all real-valued matrices of dimension m by n. Sum of two matrices, A plus B, is defined element-wise. That is, we add the entries of A to the entries of B that are in the same spot. In order to do this, obviously, A and B have to have the same dimensions. Here's an example. If we take the matrix 1, 2, 3, 4 and add it to the matrix 5, 6, 7, 8, you get 1 plus 5, 2 plus 6, 3 plus 7, 4 plus 8, or 6, 8, 10, 12. If A is an m by n matrix of real numbers and B is an n by k matrix of real numbers, then we define their product as C equals A times B. The resulting matrix is m by k, and the entries are Cij equals the sum of AIL BLJ, where our sum runs from L equals 1 to n. What this means is that we take the rows of A and the columns of B and multiply term by term and add up those products. Note, matrices can only be multiplied if their neighboring dimensions match. So for example, we can multiply a matrix that's m times n by a matrix that's n times k because the neighboring ends match. The result is a matrix that's m by k. Here's an example. We'll let A be the 2 by 3 matrix, 1, 2, 3, 3, 2, 1, and B be the 3 by 2 matrix, 0, 2, 1, negative 1, 0, 1. We can multiply terms in the first row of A by terms in the first column of B. So 1 times 0, 2 times 1, 3 times 0, and add those up. So 0 times 1 plus 2 times 1 plus 3 times 0 is equal to 2. That becomes the entry in the 1, 1 spot in the resulting product matrix. We can then take row 1 of A and column 2 of B. 1 times 2 plus 2 times negative 1 plus 3 times 1, and that gives us 3. So that's the term in the first row, second column of our product matrix. Then we can take the second row of A, first column of B, and go 3 times 0, 2 times 1, 1 times 0, and that gives us a 2 in the second row, first column entry of the product matrix AB. Finally, we can go 3 times 2, 2 times negative 1, and 1 times 1, multiplying the second row and second column of A and B respectively. That gives us 5, and that sits in the second row, second column of the AB product matrix. because A is 2 by 3 and B is 3 by 2, the neighboring 3's match, and so we're able to compute this product. The result is 2 by 2. Note, however, that if we take matrix B, which is 3 by 2, and matrix A, which is 2 by 3, we can multiply B times A. Since the neighboring 2's match, we can compute their product, and the resulting matrix is going to be 3 by 3. So go ahead and repeat that same process, and you get the matrix 6, 4, 2, negative 2, 0, 2, 3, 2, 1. It's worth noting here that you can compute the product of A and B if their dimensions are different. They just have to have that matching dimension, matching neighboring dimension. We can also see here that matrix multiplication is not commutative because AB isn't equal to BA. In fact, the product AB doesn't even need to have the same dimensions as BA. In n by n space, the identity matrix is defined to be the matrix that has 0 in every entry except down the main diagonal. The entries on the main diagonal are 1. This is an important matrix in linear algebra because it acts in the same way as multiplying a number by 1 does. It leaves the number, or in this case the matrix, unchanged. 3 important properties of matrices that we should all know. They're associative. So, assuming that the dimensions work out, so A is m by n, B is n by p, and C is p by q, A times B times C is equal to A times B times C. They're distributive. Again, assuming that the dimensions work out, A plus B times C is equal to AC plus BC, and A times C plus D is equal to AC plus AD. Finally, for any matrix A, the identity matrix times A is equal to A times the identity matrix, which is equal to A. In our next video, we'll talk about some other properties of matrices, such as a matrix transpose, and we'll use some of these properties to solve or to set up the properties that we can use to solve systems of equations using matrices.